Have you ever wondered what the entire universe is made of? Well, it turns out, from the tiniest atom to the biggest galaxy, it's all built on just a few surprisingly simple rules. And today, we're going to uncover that fundamental recipe for, well, for everything. Let's dive in. Okay, so let's start with a little riddle. What could a giant cloud of gas, a speeding bullet, and our own planet Earth possibly have in common? It sounds kind of random, right? But the answer actually reveals a deep, fundamental truth about how our universe works. And by the end of this, you'll see the hidden thread that connects them all. So the answer to that riddle, and to how pretty much everything is built, it all starts at the smallest possible scale, with the atom. You see, it turns out there's this one core rule, a really simple pattern of behavior that dictates how all matter, well, how it behaves. So this is our starting point, and it's a simple idea, but it's also incredibly profound. Everything you can see, everything you can touch, you yourself, it's all just a massive collection of atoms that are constantly, endlessly moving, vibrating, and interacting with each other, nonstop. And this right here, this is the simple rule that governs all that motion. It's called the intermolecular potential. The best way to think about it is like a universal social distancing rule for atoms. They're kind of drawn to each other when they're a little ways apart, but they absolutely repel if you try to push them too close together. This constant little dance of push and pull is the engine for everything we're about to see. Let's just break that down for a second. When atoms have some comfortable space between them, there's this gentle little pull, sort of holding them together. But if you try to force them too close, they push back, and they push back hard. This simple, constant back and forth of attraction and repulsion is what gives all matter its structure and its form. So what's the first big consequence of this atomic dance? Well, it's something you see every single day. It directly creates the three familiar states of matter. Think about it. In gases, the atoms have so much energy that they just overcome that weak attraction and bounce around like a wild game of cosmic pinball. In liquids, that attraction is just strong enough to keep them all together, but they can still kind of slide and flow past each other. And then in solids, the atoms are locked into this tight, vibrating grid, held perfectly in place by that balance of push and pull. So the key takeaway here is they're not different things. They're just the same atoms behaving differently because of that one simple rule. Okay, this is where it gets really, really cool. That atomic vibration we just talked about, it's not just one thing. It's actually a whole spectrum of phenomena that we experience as completely different things: motion, sound, and even heat. All right, let's start at the low-frequency end of the spectrum. I want you to imagine all the atoms in an object vibrating perfectly in sync, with a wavelength so long it covers the entire object. What does that look like from our perspective? It just looks like the object itself is moving. That speeding bullet from our opening riddle? Yep, that's just trillions upon trillions of atoms all vibrating together in one direction. Now, as we shorten that wavelength, the vibrations stop moving the whole object and instead start traveling through it as these organized waves. And we perceive these waves as sound. This is literally what's happening inside a guitar string or in the air when we talk. It's just waves of atoms pushing on each other. And the relationship here is just crystal clear. A long, kind of lazy wavelength gives you a low-frequency, deep bass sound. A short, frantic wavelength creates a high-frequency, high-pitched sound. It's all the exact same phenomenon, just different speeds of atomic vibration. So what happens when we shrink those wavelengths all the way down to the absolute smallest scale, to the highest possible frequencies? Well, the vibration stops being an organized wave and it becomes completely random, chaotic jiggling. And that microscopic, chaotic energy is something we experience every single day. We call it heat. This quote from the source material just blows my mind every time I read it. It says if you could somehow remove all those tiny, high-frequency vibrations, which are basically the highest-pitched sounds inside a material, you would remove all of its heat. Its temperature would literally drop to absolute zero. That's how deep the link between sound and heat really is. So far, this one rule of the atom has explained everything from what a solid is to what heat is. But to understand planets and galaxies, we need to add one more ingredient to our recipe: a surprisingly feeble touch of gravity. You know, on the scale of you and me, gravity is unbelievably weak compared to the atomic forces holding our bodies together. But here's the trick with gravity. It accumulates. As you gather more and more atoms together, its effect adds up and up and up until it becomes the most powerful force in the game. And the power of all this accumulated gravity is just staggering. It's the force that pulls these unimaginable collections of matter, like planets and stars, into almost perfect spheres. It's the cosmic glue that holds our entire solar system together in this delicate, stable dance. It really directs the whole grand cosmic ballet of orbits. So, we now have our two ingredients, the push and pull of atoms and that persistent, ever-growing tug of gravity. With just these two simple rules, we can actually write the recipe for building an entire universe. That's right, just those two principles, the atomic push and pull and gravity, that's all we need to tell the story of cosmic creation, from a totally formless cloud of gas to the magnificent, sprawling galaxies we see in the night sky. So here's the four-step recipe. It all starts with a huge cloud of gas that begins to cool down. That allows our atomic rule to form the very first tiny grains of dust. Next, these grains start bumping into each other and sticking together, forming bigger and bigger clumps. Then, as these chunks get really massive, gravity finally takes over, pulling them into orbits around one another. And finally, over immense spans of time, this cosmic dance creates the vast, intricate web of galaxies and solar systems we see today. And the end result of this simple little recipe is absolutely breathtaking. It's the universe we know and love, with its beautiful spinning galaxies, its brilliant stars, and complex solar systems filled with planets and moons and comets, all of it held together by that delicate balance of atomic forces and gravity. But here is the absolute best part. This isn't just some neat theory. When we point our telescopes up at the sky, the large-scale structure that we actually observe out there, it perfectly matches what this simple two-rule model predicts. These simple ideas really did build our complex reality. So that brings us all the way back to our first question. A gas cloud, a speeding bullet, and the Earth, they're all just different arrangements and scales of atoms following the exact same simple rules. It really makes you wonder, doesn't it? If two simple rules can build our entire universe, what other profound connections are hiding in plain sight, just waiting for us to look at the world on a different scale?